Turn next to the second law of thermodynamics. And we build the second law of thermodynamics on the back of the first law of thermodynamics. And remember, when we looked at the clarification that the first law of thermodynamics brought us to separating the system from the surroundings, we recognized that in analyzing the heat and work delivered from the surroundings to the system, that we had to be very careful about our conservation of energy. And so when we move to the second law of thermodynamics, it's based on a remarkably simple statement, and that is that any spontaneous process in nature results in an increase in the entropy of the universe. That is to say, if we write delta S, the change in entropy of the universe, that's equal to the change in entropy of the system plus the change in entropy of the surroundings. And in particular, we're going to analyze the flow of heat from the system into the surroundings. So it's heat that's leaving the system. Now remember our rule that when we look at the system, that the heat going in is greater than zero, and the heat going out is less than zero. What we're concerned about here is stating the second law of thermodynamics, that is, any spontaneous process in nature results in an increase in the entropy of the universe. And that means we're going to focus specifically on eliminating the change in entropy of the surroundings. And we do that by recognizing that Q, the heat leaving the system, is identical in magnitude through the conservation of energy, but opposite in sign to the heat entering the surroundings. And we can then write the fact that delta S of the surroundings is equal to the heat that enters the surroundings divided by the temperature at which that heat was exchanged. But because the heat entering the surroundings is equal but opposite in magnitude to that leaving the system, we write this as minus Q of the system, again divided by the temperature. We also know that under constant pressure conditions, the heat leaving the system is also identically equal to the change in enthalpy of the system, again divided by the temperature. So let's write our second law, which is to say the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. But now we have an expression for the change in entropy of the surroundings in terms of the system. That is, we can write this as minus the change in enthalpy of the system divided by the temperature. And the second law says that for any spontaneous process, this quantity must be greater than zero. I can rewrite this then as the change in enthalpy of the system minus the temperature times the change in entropy of the system must be less than zero for a spontaneous process. Look at how simple that argument is. It takes a law that on the face of it is quite abstract, that is, any spontaneous process in nature results in an increase in entropy of the universe, and it converts it into a highly specific calculation because we can calculate both the change in enthalpy and the change in entropy. And look how simple that is.